Welcome to the video lecture on operating systems CST206. In this video lecture, I'll be discussing about semaphores, which comes under process synchronization in module 3. Before diving deep into the concept of semaphores, we have to understand why semaphores were introduced. Earlier, synchronization problems were solved using hardware-based solutions, but it created a problem among application programmers. In order to create a software based solution for synchronization problems, the concept of semaphores was introduced by the famous Dutch scientist Sahrdaya. Now let us look into the definition of semaphores. A semaphore, yes, is an integer variable used in mutual exclusive manner by various concurrent cooperative processes in order to achieve synchronization. Semaphore is simply a variable which is non-negative and shared between threads. The variable is used to solve critical section problem and to achieve process synchronization in the multiprocessing environment. So the point to be noted over here is that semaphore, which is denoted as S, is an integer variable. A variable is something that stores a value, and here in this case it is an integer value, and it is used in mutual exclusive manner by various concurrent cooperative processes, and it is used in order to achieve synchronization. And also we have to understand that semaphore is a non-negative value and it is a shared variable. It is shared between different threads or processes. Also, this variable is used to solve critical section problems and ultimately to achieve process synchronization, particularly in multiprocessing environment. Now let us look on to the characteristics of semaphore. So as I said, it is a mechanism that can be used to provide synchronization of tasks. Also, it is a low level synchronization mechanism. Now, semaphore will always hold a non-negative integer value as said in the definition. And also, semaphores can be implemented using test operations and interrupts, which should be executed using file descriptors, which will be discussed deeply in the upcoming slides. Now, a semaphore S is an integer variable that apart from initialization is accessed only through two standard atomic operations, which are wait and signal. So in order to access a semaphore, we have to use two standard atomic operations, which is wait and signal. Wait is denoted as P, which comes from the Dutch word proberen, which means to test, and signal is denoted as V, which comes from the Dutch word verhogen, which means to increment. Let us now look into the definition of the wait operation. The wait operation is defined as such. Here, P denotes the wait operation and S denotes the semaphore value. So whenever a process is trying to access the semaphore value via the wait operation, it checks the condition whether S is less than or equal to 0. And if the condition is satisfied, it enters the while loop, and within the while loop there is a semicolon, meaning that there is no operations to be executed. And in case if the condition is not satisfied, that is when S is greater than 0, it exits the while loop and the value of the semaphore is decremented. Now, what does this operation actually signifies? See, whenever a process is trying to access the semaphore value, in case if the semaphore value is less than or equal to 0, then the process gets stuck within this loop and it cannot enter the critical section area or it cannot access the resources. And in case if the value of S is greater than 0, then the process exits the while loop and the value of the semaphore is decremented. That means the operation is open to access the resources and enter the critical section area. So we can say that the wait operation actually checks or it tests whether or not an operation is able to enter the critical section area or is able to access the resources. So whenever the value of s is less than or equal to 0 is satisfied, that means that some other processes is actually utilizing the resources or is accessing the critical section area. So the process in the current waiting state should stay within the loop. This is what the wait operation signifies. Now let us look on to the definition of the signal operation. See, in the signal operation, what happens is it just increments the semaphore value. The value of s is getting incremented within the signal operation. So the signal operation will be called when the process that was making use of the semaphore to enter the critical section or was using the resources completes the operation and comes out of it. At that moment, the signal operation will be called and the value of the semaphore gets incremented. Once the value of the semaphore gets incremented, what happens is it signals other processes that the semaphore value is now free to use by the processes. That means the value of the semaphore is released, and now any processes that are trying to access the semaphore value is free to access it. That is why signal operation is called signal. It actually signals other processes that the semaphore value is released and any other processes can make use of it. So this is the definition of the signal operation. Now let us look on to an important note. All modifications to the integer value of the semaphore in the wait and signal operation must be executed indivisibly. What does that mean? It means that when one process modifies the semaphore value, no other process can simultaneously modify that semaphore value, right? So once a process is using a semaphore value, then no other processes can simultaneously modify that same semaphore value. It is clear. Okay. Now let us look on to a working flow of a semaphore or how it is implemented. See, as I said, whenever a process is trying to access a semaphore value via the wait operation, it checks the semaphore value. It checks whether the value of s is less than or equal to 0. In case if that condition is satisfied, the operation gets stuck or the process gets stuck within the while loop, which means it stays in the waiting queue. Once the condition is not satisfied or if s is greater than 0, it breaks out the while loop and it enters the critical section area or it uses the resources. Once the process uses the critical section area or have accessed the resources, it then calls the signal operation. And within the signal operation, what happens is the value of the semaphore is incremented. Once the value of the semaphore is incremented, what happens is it signals the other processes that the value of semaphore is released and any other processes are now free to access it. Okay, so this is how a semaphore is implemented. Now let us look on to the types of semaphores. There are two types of semaphores: counting semaphore and binary semaphore. Binary semaphore, it can have only two values, 0 and 1. Its value is initialized to 1. It is used to implement the solution of critical section problems with multiple processes, also known as mutex locks, as they are the locks that provide mutual exclusion. So binary semaphores are those semaphores that can have only two values, either 0 or 1, and it is said that it is initialized to 1. To understand the working of a binary semaphore, we will take the working flow of a semaphore. Consider a scenario in which the critical section or the resources are not being used by any resources initially. Now let us say that a process 1, say P1, is trying to access the critical section area or the accessing the resources. So as I said, in binary semaphore, the semaphore value is initialized to 1. So it checks the condition while s is less than or equal to 0. So the condition is not satisfied and the value of s is decremented. So the value of semaphore, which is initially 1, becomes 0, and process P1 enters the critical section area and it uses the resources. Okay. Now at the same time, if a process, say P2, is trying to access the critical section area of the resources. This is scenario 2. In that case, what happens is the value of S is right now 0. So what happens is P2, it checks the condition S is less than or equal to 0. Yes, the condition is satisfied, and the process P2 gets stuck inside the while loop, which means it stays in the waiting queue. And process P1 at the same time, scenario 1, is now executing the critical section, or it is accessing the resources. Now once the process P1 exits the critical section area or have used the resources, now it calls the signal operation, and within the signal operation, what happens, the value of the semaphore S is incremented, which means right now the value of S becomes 1. At the same moment, in scenario 2, the process P2 is inside the while loop, okay, trying to access the critical section area. Now when process P1 exits the critical section area or have accessed the resources and increments the value of the semaphore, what happens is process P2 exits the while loop, and then it decrements the value of S to 0 again, and it enters the critical section area. What happens over here, once the process P1 exits the critical section area and incremented the value of semaphore using the signal operation, the process P2 couldn't access the critical section area, right? Once it exited the critical section area, which means the process P1 exited the critical section area and incremented the value of semaphore, process P2 could access the critical section area or the resources. This is how binary semaphore works. Now let us look on to counting semaphore. The value can range over an unrestricted domain. It can be used to control access to a resource that has multiple instances. So in counting semaphore, it can take up any value, okay, and it is usually used in cases when the resources are having multiple instances. So for understanding the working of a counting semaphore, we will go back to the workflow of a semaphore. So I said it is used in cases when the resources are having multiple instances. So say the resources are having two instances, say R1 and R2, and there are two processes P1 and P2 that want to access these resources respectively. So since we have two instances for the resources, we initialize the value of S to be 2, and say process P1 is trying to access the resources. So P1 checks the value of S, and 2 is less than or equal to 0. The condition is not satisfied, and the value of S is decremented, and process P1 enters the critical section area and it utilizes the resource R1. At the same time, say a process P2 is trying to access the critical section area. Now the value of S is 1, and the condition is not satisfied, and again the value of S gets decremented, so 1 becomes 0, and process P2 also enters the critical section area and utilizes the resource R2. Similarly, if a process P3 is trying to access the critical section area or want to access the resources, what happens is it again checks the value of S, and now the semaphore value is 0, and the process P3 gets stuck inside the while loop. And in case if process P1 has finished utilizing the resource R1, it exits the critical section area and calls the signal operation. And when the signal operation is called, the semaphore value S is incremented and it becomes 1. And the process P3, which is gets stuck inside the while loop, exits the while loop since the condition becomes false. And again, S decrements and process P3 can also utilize the resources. So this is how counting semaphore works. Now let us look on to some disadvantages of semaphore. See, the main disadvantage of semaphore definition discussed before was that it requires busy waiting, right? While a process is in its critical section, any other process that tries to enter its critical section must loop continuously in the entry code. Whenever a process is trying to access the semaphore value, at the entry code, what happens is if the semaphore value is less than or equal to 0, what happens is it gets looped inside the while while loop continuously, right, until and unless the semaphore value is incremented or the other processes have utilized the resources of the critical section area. That particular process gets looped inside the while loop. and this results in busy waiting. And what is one of the disadvantage of busy waiting? Let's see. Busy waiting wastes CPU cycles that some other processes might be able to use productively. That means the moment a process gets looped inside the entry code in that particular while loop, at that same moment CPU is also being used for looping inside the while loop. So until that process gets exited from the while loop, up till that moment the CPU is also being utilized for that looping process, right? So that busy waiting caused due to looping also results in wasting a precious CPU cycles which could have been used by other processes productively. So that is one of the disadvantage of looping and busy waiting. And this type of semaphore is also called a spin lock because the process spins while waiting for the lock. So this type of semaphores which results in busy waiting by looping inside the entry code is also called as spin lock because it spins while waiting for the lock. Okay. Now let us see if we can find any solution for busy waiting. To overcome busy waiting, can we find any solution? Let us look in the further slides. Okay, so to overcome the need for busy waiting, we can modify the definition of the wait and signal semaphore operation. So by making a simple modification, we can overcome the concept of busy waiting, the disadvantage of busy waiting. So let us see how it is done. When a process executes the wait operation and finds that the semaphore value is not positive, it must wait. Yes. So how it can be overcome? Let's see. See, however, rather than engaging in busy waiting, the process can block itself. The block operation places a process into a waiting queue associated with the semaphore, and the state of the process is switched to the waiting state. That means instead of a process getting entered into a while loop and looping inside it, we can block the process itself. How can we do that? The block operation places a process into a waiting queue. So instead of getting inside the while loop and looping inside it, the process which is trying to wait is shifted to the waiting queue and it is not looped inside the while loop. So it is done using the block operation, and what we are doing is that the state of the operation which is waiting in the waiting queue is switched to the waiting state. By doing this, what happens is we can block a process from getting looped in the entry code. And then what we do is then the control is shifted to the CPU scheduler which selects the another process to execute. So this is what happens when we modify our wait and signal operation. We can make slight changes and it results in saving our precious CPU cycles, and it can be utilized productively by other processes. So instead of a process getting looped inside a while loop, we can block that process and we can make that process wait inside the waiting queue and also change the state of the process to the waiting state. Then what we do is we transfer the CPU scheduler. Okay, we then we transfer the control to the CPU scheduler, and also the CPU scheduler then select which process is needed to be executed next. By doing this, we can uh, overcome the problem of busy waiting. Now we have discussed that by introducing some slight modifications on the wait and signal operation, we could solve the problem of busy waiting. That was done by introducing waiting queue. But there are some other problems that we are going to face even after introducing the concept of waiting queue. Let us see what it is. The implementation of a semaphore with a waiting queue may result in a situation in which two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. That is, when we have introduced the concept of waiting queue, there can be chances or there can be situations in which two or more processes are waiting indefinitely for an event. That means when two processes are waiting indefinitely for the same event to occur, but it can only be solved when one of the waiting process is executed then in that situation there comes a condition called deadlock. That means when two processes are waiting for the same event to occur, but only one process can execute further and resolve the problem. But in situations where both the processes are waiting indefinitely and nothing occurs further, this condition is known as deadlock. The event in question is the execution of signal operation. When such a state is reached, the process are said to be deadlock. That means when the waiting operation is not executed further, then the signal operation is not going to be executed as well. And when the signal operation is not executed, then we are not going to increment the value of the semaphore, and hence nothing is going to happen further. Such a situation in which nothing happens due to an indefinite waiting of two or more operations in the waiting queue is known as deadlock, and deadlock results in starvation. For understanding the concept much better, I will have given up two examples over here with a process P0 and process P1. Here, this is a code for process P0 where we have to execute a wait operation with semaphore S, and also we have to execute a wait operation with semaphore Q. And also, after executing the code, we have to uh, implement the signal operation on the semaphore S and the signal operation on semaphore Q. Similarly, we have a process P1 uh, which is going to execute the wait operation on semaphore Q initially, then on semaphore S, then to run the code, and it is going to execute the signal operation on Q and then signal operation on S. So this is the situation. So let us consider initially process P0 have executed the wait operation on semaphore S, and at the same time process P1 has executed the wait operation on semaphore Q. So far so good. There is no problem on executing the wait operations up till now. Now the process P0 is trying to execute the wait operation on semaphore Q, but this is not going to happen because process P1 has hold on the value semaphore Q, and it is not released yet since signal operation on Q is not executed. At that moment, the process P0 is not able to execute the wait operation on semaphore Q. Similarly, when process P1 is trying to execute the wait operation on semaphore S, it is not going to happen because the semaphore value S is being held by the process P0. That means both the operations P0 and P1 is waiting indefinitely for the next operation to be held. Since process P0 is waiting for semaphore value Q to be released by process P1, and since P1 is waiting for the semaphore value S for the value S to be released by process 0, both are not going to happen at the same time. And at that moment, what happens is the signal operation is not being executed and both the processes are said to be deadlocked. So there are situations in which this could happen, and this is one of the disadvantages of a semaphore. And the concept of deadlock results in starvation, meaning that no processes are going to be executed further and the process stay deadlocked. So I hope you have got a clear idea on deadlock and starvation and the other concepts related to semaphores. So as a summary, I could say that we have discussed about the definition of a semaphore. We understood the basic definition of semaphore. We understood who introduced semaphore and why a semaphore was introduced. We studied about the basic characteristics of a semaphore. We studied about the two standard atomic operations, which are wait and signal. We defined the wait and signal operation. And we also studied about the two types of semaphores, which is binary and counting semaphores. We studied about the definition of the binary and counting semaphores. And after that, we studied about the working principle or the implementation part of the semaphore using a wait and signal operations. Later, we studied about the disadvantages of the semaphore, which was busy waiting and wasting of CPU cycles. Later, we studied the introduction of waiting queue for solving the problem of busy waiting. And even after introducing the concept of waiting queue, there was problems like deadlock and starvation that was resulted due to indefinite waiting of two or more processes within the waiting queue. So this is a basic overview on semaphore and the concepts related to it. I hope the video lecture was clear and beneficial for you. Thank you very much.